Okay, so this lesson is section 2.2, basic differentiation rules and rates of change. In 2.1, we learned what a derivative is, and we learned the limit definition of the derivative. So taking the limit as h approaches 0 of the difference quotient in order to come up with that formula that we can use in order to calculate the slopes of the tangent lines to different points on the curve of our original function, or used to calculate instantaneous rate of change. But now you've used the limit definition for a couple days. You have earned the right to use the shortcuts. And I know some of you have really been waiting for this. So we're going to start exploring the different differentiation rules. We're going to look at the very basic ones in this lesson. So the first one is the constant rule, the fact that the derivative of a constant function, which a constant function represents a horizontal line, is equal to 0. If we think about what the derivative is, which is a formula that would allow you to calculate the slopes of the tangent lines to the curve, well, horizontal line, every point on that line has a slope of 0. So it makes sense that the derivative of the constant would be 0. We can easily prove that using the limit definition as well. So if we have f of x equals to c, then f prime would be the limit as h approaches 0. There's nothing to replace, to substitute x plus h in for. So we can write this just as c minus c all over h, which c minus c would end up being 0. 0 over h would just be 0. So you end up taking the limit as h approaches 0 of 0. So the derivative of a constant function will always be 0. Now, you can pause this video and do the exploration. Use the limit definition in order to find the derivative of y equals to x, and y equals to x squared, and y equals to x cubed. And then you can take a guess at what the derivative of y equals to x to the 4th would be, or y equals x to the 10th would be, without using the limit definition. So pause the video right now. Use the limit definition to find the derivatives, or at least do y equals to x and y equals to x squared and see what you get. And then see if you see the pattern before you go to the next page. So pause. Okay, so what you should have seen is you would have ended up guessing that dy over dx of x to the 4th was 4x cubed, and that dy over dx for y equals x to the 10th would be 10x to the 9th. So power rule is if you have a function that is in the form x to the nth power, then power rule says that the derivative of x to the n, you bring the n forward, you bring the n down, and then you subtract 1 from the exponent. So if we're finding the derivatives of these following functions, okay, so for y equals x to the 23rd, think about trying to do that by hand using the limit definition would be ridiculous. Trying to expand x plus h to the 23rd power would be crazy. But using power rule, super easy to find the derivative. So you get y prime, or dy over dx would be, bring the 23 down, subtract 1 from the exponent, so 23x to the 22nd power. To find the derivative of g of x equals to the square root of x, let's rewrite the square root of x using an exponent instead, so x to the 1/2 power. Well, now we're set up to think power rule for finding g prime. We bring the 1/2 forward and then subtract 1 from the exponent to be negative 1/2. Now it would be nice to simplify this so that we don't have the negative exponent. So thinking exponent rules, I'm going to bring x to the 1/2 to the denominator in order to get rid of the negative exponent. You can also think of that as 1/2 root x. If you want to rationalize the denominator, go for it. And then for h of x, I'm going to rewrite 1/x so that it's in the form as x to the n power. So I'm rewriting 1/x as x to the negative first power, thinking about exponent rules. So h prime would be negative, that's like bringing the -1 forward. Subtract 1 from the exponent, it's -2. And then rewriting that without the negative exponent, I would just be moving x squared to the denominator. So if we want to find the slope of the graph of y equals x cubed at x equals to 5, well, first of all, we need the y. Oh, we don't. It's not asking for a tangent line. Sorry, it's just asking for the slope. So we need the derivative, right? The derivative is our formula for calculating the slope of the tangent lines in the graph. And the slope of the tangent lines we use as the slope of the graph. So we need dy/dx. And we can just use power rule now. Super handy, right? So 3x squared after applying power rule. And then we want to evaluate dy/dx. That's going to be the slope of our tangent line at x equals to 5. So we're evaluating dy/dx at x equals to 5. So that's how you can write that. So when we plug in 5, we get 25 times 3, so 75. So the slope of the tangent line, or the slope of the graph at x equals to 5 would be 75. Okay, now we can find the equation of the tangent line. To find the equation of the tangent line, we need a point and we need a slope. To find the point, we can find f of -4 to find the y-coordinate, right? This would be the y-coordinate. That would be 16. -4 squared would be 16. And then we need f prime for finding the slope of the tangent line. So power rule, bring the 2 down, subtract 1 from the exponent. That's just 2x. So the slope of the tangent line, we can evaluate f prime at -4. And we would get 2 times -4 is -8. So now we have our point and we have our slope. So y minus 16 using point slope form equals to -8 times x plus 4. There's our equation of our tangent line. Okay, the constant multiple rule basically says if you have a function that you can think of as being like that power rule form, x to the n power, but it's times a constant, and this is going to translate beyond power rule as well. So basically, if you have a function times a constant, you can think about pulling that constant out, taking the derivative of the function, and then just multiplying it by the constant. So, for example, all of these examples are involving power rule. That's why I mentioned power rule. To find j prime, there's a 7 there. The 7 is going to then be multiplied by the 4 when we think about pulling the 4 out front or bringing the 4 down. So 7 times 4 is 28. Subtract 1 from the exponent. Done. And then we want to rewrite 2 over x squared as 2x to the -2nd power before we think about taking the derivative so that we can apply power rule. So y prime when we bring the negative 2 down, we can think about multiplying it by 2. So that would be negative 4x to the negative third when we subtract 1 from the exponent. And then just rewriting that without the negative exponent. Just good practice. Okay. And then you can leave f of x as is, or just to kind of have it in the form where you're thinking of 3/2 as being the coefficient. So then when you find f prime, you'll multiply 3/2 by 5, which will be 15/2. Subtract 1 from the exponent to get 4. And I would rewrite 2 times the cube root of x as 2x to the 1/3 power. So then when we go to find h prime, 2 times 1/3 would be 2/3. Subtract 1 from the exponent, which is subtracting 3/3. So that exponent will be negative 2/3. And then to write without the negative exponent, we could bring the x to the 2/3 to the denominator. Okay, in order to rewrite the function in E so that we can think about using power rule, I'm going to think of 1/4 as being the coefficient, and then I'm going to think of the square root as to the 1/2 power, and then bring to the numerator so that it's x to the negative 1/2 power, just so that we can think about applying power rule. So dy over dx, 1/4 times negative 1/2 would be negative 1/8, and then subtracting 1 from the exponent, that would be negative 3/2. And then last step, let's just rewrite without that negative exponent. So moving x to the 3/2 to the denominator with the 8. So we can combine the constant multiple rule and power rule into one rule, where you can just think, okay, if you have a function of the form of a constant, that constant could be 1 times x to the n power, then power rule says that the derivative would be the constant times n times x to the n minus 1 power. Okay, sum and difference rules. And this should make sense, right? Like we had our limit properties where if you had a function that you could think of as a sum or difference of other functions, you could just think about taking the limit of each part of the sum or the difference. And a derivative is a limit. So it should make sense that whenever you have a function that you could think of as a sum or a difference, you can just think about applying the shortcuts to find the derivative of each part of the sum or difference. This will kind of expand, so like polynomial functions, we can easily find the derivative by just thinking about finding the derivative of each term. So y prime here, thinking about the derivative of x cubed, would be 3x squared. The derivative of negative 2x, remember, x is raised to an exponent of 1. So when we take the derivative, that would be negative 2, and then think of it as x to the 0th power when you subtract 1 from the exponent, which would just be 1. That's why you don't have to write it. And then the derivative of a constant, 10, is just 0. So the derivative y prime is 3x squared minus 2. Okay, and then to find f prime here, so the derivative of negative 4x to the 5th, that'll be negative 20x to the 4th. This is like having 1/2 as the coefficient to x squared. So 1/2 times 2 would be 1, and then subtracting 1 from the exponent just leaves us with x. and then minus, when we take the derivative of minus 3x, that'll just be minus 3. Another perspective, there's the perspective of thinking that as an exponent of 1 and then subtracting 1 from the exponent, x to the 0th power would be 1. But there's also, this is just a linear term, and the slope of the tangent line at any point on a line would be whatever the slope of that line is. And if you're looking at negative 3x, that slope would be negative 3. This looks different. Before we can apply power rule, you can't just take the derivative of the numerator and the derivative of the denominator. We have the rule that you can take the derivative of the parts of a sum or difference, but that's not the case for if you have like a rational function, a function that is a fraction. So we need to rewrite this in order to use power rule. I would split this up into multiple fractions. So 3x squared over x minus 2x over x plus 8 over x, and then simplify. So that's 3x minus 2, and then I'm going to rewrite 8 over x as 8 times x to the negative first to think about using power rule. So y prime would then be 3 for the derivative of 3x, derivative of negative 2 is 0, and then derivative of 8 times x to the negative first would be negative 8x to the negative second power. And then just rewriting that without the negative exponent. Three minus 8 over x squared. Okay, derivatives of sine and cosine. My suggestion, I'm going to show you how to derive the derivative of cosine. The derivation of the derivative of sine is very similar, and it is in your textbook if you're interested. But I'm going to show you how to derive the derivative of cosine using the limit definition. But I would just memorize these. Know that the derivative of sine is cosine. The derivative of cosine is negative sine. So, okay, let's, in order to derive our derivative of cosine using the limit definition of the derivative, we're going to use a fundamental trig identity, one of them that I like and have a chant for. And then we'll also use our special limits that you have memorized. Okay, so for finding the derivative of cosine with respect to x, this is one way. Instead of being like, oh, y equals to cosine of x is our function we're taking the derivative of. So dy over dx would be, this states on the left-hand side here that I'm taking the derivative of cosine with respect to x. So that's going to be equal to the limit as h approaches 0 of cosine of x plus h minus cosine, and maybe right away you're like, oh, I know what identity we're going to use. Because looking at this, you're like, well, what do I do? Well, we have cosine of a sum. So this is, we'll get to use our chant sine, cosine, cosine, sine, cosine, cosine, sine, sine. The cosine, cosine, pause to switch the sign, sine, sine. So limit as h approaches 0 of, I'm rewriting cosine of x plus h as cosine of x, cosine of h, minus sine of x, sine of h, minus cosine of x, all over h. You've dealt with these type of limits where you need to like rearrange things, see if you can identify those special limits. So let's put all of our cosine, let's split this into two fractions, and let's have one fraction where we have all of our cosines in the numerator, and then the other fraction, all the sines. So we'll have the limit as h approaches 0 of cosine x cosine h minus cosine h all over h. And then I'm also going to, since we're splitting this into a difference of two fractions, I'm going to think about taking the limit of each of those fractions. Okay, so from here, notice that we have a common factor of cosine of h. Now, this is the limit as h approaches 0. So cosine of x and sine of x, we can actually treat like constants and think about pulling them out front of the limit. You don't have to, but I'm going to. And I'm also, oh, that should be cosine of x. Sorry. I was like, wait, why isn't this working? So I'm going to factor that cosine of x out. Sorry, this cosine of x. I'm going to factor that out like a constant. So then I would be left with cosine of h minus 1 all over h. And then I'm also going to factor sine of x out here. Okay. So cosine of h minus 1 over h, that's very close to this limit. There's just been a vertical reflection. You can recognize that that's 0, or we could think about factoring a negative 1 out so that we can match it. But it's not really going to matter, right? Because this limit goes to 0. This limit goes to 1. So then we're really just left with negative sine of x. Okay, so the derivative of cosine is negative sine. Memorize that. Derivative of sine is cosine. So derivatives involving sines and cosine. So 3 times cosine of x, you can just think about pulling the 3 out. So it's that constant multiple rule for derivatives. So y prime would be 3 times the derivative of cosine, which is negative sine. So negative 3 sine of x. This is a difference of two terms. So y prime, or dy over dx. Either notation is fine. We'd use power rule for finding the derivative of x squared. Minus the derivative of sine is cosine. Okay, so remember, functions can be used to model real-world situations where the independent and dependent variables can represent quantities, like time and the position of an object. You can think of the derivative of a function as a formula to calculate the rate of change of one variable with respect to another. Position functions describe the location or position of an object relative to the origin as a function of time. To calculate the average velocity or the average rate of change of an object over an interval of time, we can use the same method that we did for calculating slope of the secant line. So you could use slope formula, right? Change in y over change in x, change in distance over change in time. So let's look at this situation. At time t equals to 0 seconds, a diver jumps from a platform diving board that is 32 feet above water. The initial velocity of the diver is 16 feet per second. The position function that models the diver's height above the water in feet has a function of time in seconds is S of t is equal to negative 16t squared plus 16t plus 32. When does the diver hit the water? This is not a calculus question. These first few questions are actually not going to be calculus questions, but they'll be algebra questions. So let's first think about this function. S of t represents height above the water in feet for the diver. So height in feet. And then, so that's S of t. T is time in seconds. So when does the diver hit the water? Well, if S of t represents height above the water, that means that we want to know when the diver is 0 feet above the water. We want to know, we want to know at what time S of t would be 0. So we can just think about setting S of t equals to 0. This is just a quadratic equation. We can factor out negative 16. And factor. Oh, minus 2 plus 1. So we get t equals to 2 or negative 1. Negative 1 doesn't make sense, though. We're not talking about negative time. So after 2 seconds, the diver will hit the water. How long will it take the diver to reach the highest vertical distance above the water? This is a quadratic function whose graph is a parabola that opens down. You guys know from your prior knowledge that the vertex would be the highest point on the parabola. So we want to know at what time t, so we basically want to know what the value of t is at the vertex. So options, the vertex you can use x equals negative b over 2a or t equals negative b over 2a. Sorry, I need some water. You can also take the average of our solutions to this previous example. You can change into vertex form. It's up to you. The equation of S of t into vertex form, it's up to you. So if you did t equals negative b over 2a, we get 1/2. So it'll take 1/2, a half second. So it will take the diver 1/2 second or 0.5 seconds to reach the highest vertical distance above the water. What is the diver's highest vertical distance above the water? Well, we would want to find what S of 1.1/2 is. So I'm going to use my calculator here. So negative 16 times 0.5 squared plus 16 times 0.5 plus 32. I get 36 feet. So the diver's highest vertical distance above the water is 36 feet. You're probably wondering, why the heck are we doing these algebra, like, 1-level questions? Well, we may need it some of these answers later in the problem, or it's good practice with, like, interpreting. Like, you're on high alert right now for calculus or specifically average velocity, but really thinking about what the function represents and how to properly answer these questions is important. So D is asking, what is the average velocity? Here we go. What is the average velocity during the first half second after leaving the diving board? So since we know that the diver reaches his max height after a half second, that means that it's the velocity, the average velocity over his rise, right? Like as he's traveling up, up, up. So to calculate over the first 5 seconds, so that would be from t equals to 0 to 0.5, our average velocity will be s of 0.5. Oh, that is helpful. See, we found s of 5 already, 0.5 already. Minus s of 0 over 0.5 minus 0. And I'm not finding the difference quotient of the function because I have slope formula. That's just so much more efficient. So s of 0.5 we saw was 36 feet. S of 0 we could easily think about finding. If we plug in 0 for t, we get 32. We've also been given that as in part of the word problem. Okay, so divided by 0.5. So we get, was that 8? We get 8, and then we have to think about units. So change in height, that's height is measured in feet, time is measured in seconds. So 8 feet per second is the average velocity. So you could say the diver's average velocity during the first half second was 8 feet per second. And we know from answering those previous questions that that's whenever he has left the diving board and he's going up, up, up before he reaches that max height. So what is the diver's average velocity between 0.5 and 1.5 seconds after leaving the diving board? Okay, so that's the interval 0.5 to 1.5. So average velocity would be s of 1.5 minus s of 0.5 over 1.5 minus 0.5. So there'll be 1 in the denominator, and then s of 1.5 would be 20. So 20 minus 36. So I get negative 16 feet per second. Oh my goodness, we got a negative value. What does that mean? Well, we knew that the previous question was like right before the interval, right before he reaches his highest height. And then after he reaches the highest height at 0.5 seconds, he's going to start his descent. So his height, as time is passing, his height above the water is going to be decreasing, and that negative indicates that. So we could say something like, it's usually best to interpret that negative. So you could say something like, the diver's average velocity between 0.5 and 1.5 seconds is how do I want to word that? I'll just say it's negative 16 feet per second. I didn't set myself up well for that. But saying something about his height is decreasing at an average velocity, right? Because velocity is a vector quantity. It has both magnitude and direction. That negative indicates direction, right? His height is decreasing at an average velocity of 16 feet per second. So you could say something like that as well. What about the diver's velocity 1 second after leaving the diving board? That's not an interval of time. That's just at 1 second. And if we try and use our same strategy of calculating average velocity, we're going, okay, S of 1 minus S of 1 over 1 minus 1. Well, that's going to result in 0 over 0, which is not helpful. Indeterminate form. So this is where our strategy for calculating average velocity does not work for calculating instantaneous velocity, which we call just velocity of an object. So instantaneous velocity of an object is just how fast an object is moving at a moment in time. And can be approximated by calculating the average velocity over a small interval where you think about making that interval smaller and smaller and smaller. Using delta t here instead of h, you could also think about using h. That would be fine, right? Like saying instead h approaching 0 and use h here and h here. That doesn't matter. It represents the length of the interval. So remember, velocity is a vector quantity, has both magnitude and direction. Therefore, velocity can be negative, 0, and positive to indicate direction, and the speed of the object is the absolute value of the velocity, right? The absolute value of the velocity is the magnitude of the velocity, which would represent speed. So we're using the same example as above. What is the diver's velocity 1 second after leaving the diving board? Well, we need to calculate instantaneous rate of change. So we need to calculate the slope of the tangent line to the curve of S of t at t equals to 1 second. So I'm going to come back up to my function. I'm going to copy and paste it to reference down here. There we go. So now we don't need to use the limit definition to find S prime of t. Yay! We can just use power rule. So that'll be negative 32t plus 16. So S prime of 1 would be negative 32 plus 16, so negative 16. And the units would still be feet per second, just like average velocity, right? Because change in different distance over change in time. So we could say the diver's velocity 1 second after leaving the diving board is 16 feet per second. So that also, we got a positive velocity that tells us that his height is increasing at that moment in time. Oops, didn't mean to erase that. Positive sloping tangent line means his height would be increasing. What's the diver's velocity after 0.5 seconds? Interesting. We know what happens at 0.5 seconds. He reaches his max height. Well, if we plug in 0.5 or 1/2, we get 0 feet per second. His velocity would be 0. And that should make sense, right? When he reaches that max height, he goes up, 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 and then he stops for a second before he goes down, 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 and starts his descent. Oh, that shouldn't have turned into a line. So the diver, and you could even say something like the diver is not moving. Or they have 0 velocity, he's moving 0 feet per second. It's not moving at 0.5 seconds. And then what is the diver's velocity at impact with the water? How long was he in the air? Didn't we determine that in the first question? Yes, we did. He hits the water after 2 seconds. So we want to find S prime of 2. So we would get negative 64 plus 16 would be negative 48. Seems like a pretty fast speed, right? Pretty big impact for hitting the water. So you'd say the diver's velocity at impact with the water is negative 48 feet per second. And that's one of those, you could interpret that negative as well. You could say the diver's, it's kind of a funky one to say. The diver's height is decreasing at a rate of 48 feet per second at impact with the water, or something like that. Okay, so we were able to use power rule in order to find our derivative here. That was a lot faster than the limit definition, but you still need to understand that the derivative is a limit. We're thinking about taking the limit, making the interval that you're calculating average rate of change over smaller and smaller and smaller in order to calculate instantaneous rate of change.